All right. Sorry that we're doing this on video again today. Well, I guess it was just one class that we had to do that on Monday, but anyway, so with today's stuff, I am going to tell you when you should pause the video and do a practice problem. You really need to do that. You need to actually work it out, and it should be even better than in class because you're not going to be rushed along by me starting it if you're not ready. So you need to pause and do the practice problem and then come back with us. If you try to just look at the answers and think, oh yeah, I got that, it's not going to work as well because you're not going to have it, sorry, my brain is not completely there. You're not going to have it solidified in your memory as easily. Okay. All right, so this is where we stopped on Wednesday. And like I said, this is going to probably be the best way for you to not only remember the quantum numbers from chapter 8, but also to apply it now to looking at electron configurations in chapter 9. Now, the order of these orbitals should be pretty comfortable for you at this point up until we get to this thing that we talked about on Wednesday, where we have this difference in the fact that the 3p goes up to the 4s is the next orbital in energy, and then back to the 3d. So that's probably where you're going to have the most difficulty. And thankfully, the periodic table will offer a guide for that to helping you remember the order that all of these orbitals go in. Okay, so if you're struggling with that at all and worried, like, how am I going to do this if I don't have that table in front of me? The periodic table is going to offer you a guide to doing that. What it won't give you is the M sub L values, but hopefully you're getting comfortable enough now to know how each of those changes. It will help you to know how many orbitals there are. So like the method we're going to use today will help you to know that there's 3 p orbitals and that there's 5 d orbitals. And then assigning those M sub L values should be pretty straightforward, knowing that d is an L of 2 and that there's 5 of them. So you're starting negative and going through the positive values. Okay? All right. So the first practice problem that we're going to do is... And we actually did some of these the other day and maybe even some harder ones. But we're going to do carbon and oxygen. And so if you want to go ahead and practice these right now before I get started, that's probably a good point. The way I would do them is to start with the orbitals diagram. So use this as a guide. And you can even, what I'll do is probably just start and do it here and then kind of rewrite it as if I were doing it. No, I probably won't do that actually. You can use this as a guide to starting the orbital diagram if you need it. So start with the orbital diagram, then go to the electron configuration, which is where you're summarizing the orbital diagram basically in text rather than in a picture, but you're omitting the M sub L values there is the biggest thing. And really, you don't have to include the M sub L values in the orbital diagram either. Then you can kind of move from the orbital diagram up to the quantum numbers. This is probably what people still struggle with the most, but just recognize that you're doing a unique set for each electron. The N, L, and M sub L are summarizing the orbital that that electron is in, and then the M sub S is just the spin. Okay? So go ahead and pause the video now, do both carbon and oxygen, and then come back and we'll do those together. Okay, you better have paused the video. All right, so carbon. First thing is figure out how many electrons there are. So it's element number 6. It's neutral, so 6 electrons. We're going to start at the bottom like we always do with the 1s orbital, then the 2s, and then the 2p. The reason I stagger these, like they're not on top of each other like this, is because they're close enough in energy that it's not really a good description if I wouldn't have room if I wrote 1s, 2s, and 2p the way that it should be energy-wise. I wouldn't have room to write I guess I could write it over here, 2s and 2p, but then I'm leaving myself very little room for the electrons. So that's why we stagger them. It's not, I don't know, it's not for some other reason. Okay? Just going to redraw that slightly. All right, so 6 electrons starting at the bottom. I'll do these in a different color. 2 in the first one, 2 in the second one. And then remember here for Hund's rule, we separate these out into separate orbitals until we have to pair them up within a given subshell. And then we also put their spin both as being up, and it's not until we pair them that we start to put them down. Okay, so there's the orbital diagram. Electron configuration is going to label the subshell, lowest energy first, and then say how many electrons are in there. So 1s2, 2s2, 2p2. So that should coordinate with your orbital diagram. There are 2 electrons in the 2p subshell. That's why there's that 2 superscript. Okay, and now the hardest one is going to be the number of the quantum numbers for each electron. But if you use the orbital diagram as a guide, that should make it a little bit easier. So I'm going to do, and I'll try to standardize this now, I'm going to put the electron 1, electron 2, electron 3, electron 4, again going in lowest energy up to highest energy, and do this for all 6 of them. And remember, these 3 are going to tell me what orbital it is, and then the m sub s is telling me the spin of the electron in that orbital. So let me try and hit each electron individually, showing you where it is in the orbital diagram and then assigning its quantum number individually. When we've done this in class so far, I've kind of treated them as groups, and maybe I'll just treat them all separately this time. Okay, so this is my first electron here. It's in the 1s orbital, and maybe I'll go ahead and add the m sub l values to my orbital diagram. That's not a necessary component of orbital diagrams, but if we're trying to convert this into quantum numbers, it's going to be really helpful. So the subshell is written on the side, and then I'm going to write the m sub l values underneath. Remember, for an s, there's only one m sub l value because there's just that one orbital. Those 2 things are tied together. And then for the p, there's 3 of them. The p is equivalent to an L of 1. The S is equivalent to an L of 0. These are the things you have to remember from chapter 8. We're kind of using the letters now. We're not even talking about the L values. Okay. So the m sub l values, I'm writing underneath each orbital. That's a range from -1 to +1 because the L value is 1. Okay. So the m sub l's, and you'll see this on this chart above, right? These are all labeled out for you. These are the L values up here. The N values are the first ones, the first number written here, okay? The L value in its number form is here, and in its letter form is here. And then the m sub l values are written underneath the orbital. Okay, so for that first electron, back to that. The one highlighted in yellow. The N is 1, the L is 0, the M sub L is 0, and the M sub S is +1/2. It's in the 1s orbital, so that's why the N is 1. S is equivalent to L equals 0, so that's why the L is 0. When L equals 0, M sub L is always 0. There's no other choice there. And then the convention is we always write the first one as being a positive spin or an up spin, if you want to call it that, of +1/2. So that's the first electron. Second electron there, also in that same orbital. So because it's in the same orbital, all three of those first quantum numbers are the same. The only difference is the negative spin. So -1/2 for the spin on that electron. Okay, next one in the 2s orbital. So n equals 2. It's an s orbital, so L is still 0. If it's an s orbital, m sub L is always 0. First electron, +1/2. Second electron in that orbital, same for the first three numbers because the orbital is the same, -1/2 spin. Now the 2p electrons, so we'll do that first one. N equals 2. Now we're talking about a p orbital, so L is 1. And the m sub L is -1. And I see that just because I've written -1 under there. So I'm assigning that orbital to be the -1 orbital. Positive spin, so +1/2 for the spin. Now this last electron is in a different orbital. So unlike the other ones where we've said, oh, the first three numbers are all the same, those were in the same orbitals. This one's in a different orbital, a different line in our diagram. So it's still n equals 2, and it's still the p subshell, so it's still an L of 1, but now the m sub L is a different value because we're in a different orbital, so it's 0. Also a spin of +1/2. Okay, hopefully you've already paused and done this for oxygen. Here's a nice little trick. Every electron follows the same pattern. You just add more electrons. So I literally am just going to copy and paste and add 2 more electrons here. I can do the same thing with the orbital diagram. I can do the same thing with the electron configuration. I'm just going to squish these guys in a little closer so that we can make room for those other 2. Okay. I'm going to copy the orbital diagram and the electron configuration, and then I'm just adding to them. Oxygen has 2 extra electrons, so I need to account for those 2 extra electrons. Try that one more time. Copy, paste. There we go. Okay, let's get rid of some of this highlighting. Okay, so I'm just going to add 2 these. So the 2 additional electrons, so I'm in the orbital diagram. Remembering now oxygen has 8 electrons, so we're adding 2 more. So 1. Now I have to start pairing them up. 2. In the electron configuration, all that changes is the number in the 2p subshell. So I'm going to erase that 2, and now I'm going to put a 4. I just added 2 more electrons to the 2p subshell. And then finally, for the quantum numbers, so now we're doing this electron first for number 7. So n equals 2, L equals 1, m sub L, it's now in the 1 orbital. The m sub L equals 1. Still +1/2. And then for that last electron, that's where they start pairing up. So n equals 2, L equals 1. We're still in the 2p subshell. M sub L equals -1, and now it's a -1/2. To preempt someone's question, no, it doesn't matter if I like flip these. Technically, it doesn't matter if I was writing the quantum numbers for oxygen. Now, in reality, it did fill into separate orbitals first and then paired up. So it's probably more accurate to write it like this. But if you had kind of like flipped these sets, let me do that. Oh, that's not really what I meant to do. Okay, let's go like this. I just want to take those quantum numbers and move them out. Okay, so if I'd written it like this, that's not wrong. Okay, that's fine if you did it like that. And maybe if you had just started with oxygen, you would have done it like this, because you would have looked at the diagram and said, oh, there's 2 electrons in the -1. I'm just going to write those one after the other. Electron 5, electron 6, same orbital, different spins. That's fine. It's not really different. We just did it in a different order because we were coming from carbon. Okay, so this is the electron configurations and the orbital diagrams. We're not really looking at quantum numbers a whole lot more. I think I said that on Wednesday, but then apparently I did just now look at more quantum numbers. Oh well. So here's the orbital diagram and the electron configurations for the first 4 elements in the second row. And a couple things I want you to notice. They're in the second row of the periodic table. And so their valence shell, or the shell with the outermost electrons, the highest energy electrons, those are all at n equals 2. Okay, so that's one thing that they share. Another thing is we're just changing the number by 1 every time because the proton number is changing, right? If you look at the number of protons, the atomic number, this goes from 3 to 4 to 5 to 6. So the number of electrons is changing. And so in the electron configuration, as well as in the orbital diagram, we're just adding 1 more electron every time we move along a row in the periodic table. So 2s1 becomes 2s2. We can only hold 2 electrons in the 2s, so when we add another electron, we go to the 2p now, so 2p1 and 2p2. Okay, so you're just increasing it by 1 every time. So before we get to this one, let's look at the periodic table itself. And you can see this is the second row where all of the valence electrons are in n equals 2. This is the third row. All the valence electrons are in n equals 3. So if you didn't catch this, we have already talked about this a bunch of times. We're just formalizing it now. The valence electrons are the outermost principal energy level, the highest energy ones. So that's in red down here. The core electrons are the ones that are in the lower energy levels. Those are in the blue. So make sure you're clear on that. Don't worry yet about this abbreviation. We'll talk about that in a second. Okay, I've said this before, just reiterating it. Valence electrons are the primary way that we see behavior chemically, physically. Those are the biggest indicator. Okay, so that's why we're focusing on them so much. Oh, that is not actually the one I wanted to show, the periodic table, because this is just showing the valence electrons. Trying to think. Well, if you look at the first one, you would just add 1s2 to get the complete electron configuration to each of these. So it is kind of interesting. It just wasn't what I was intending. But this does show you the valence electrons for each of the elements in the second row. And then in the third row, I would have to add to each of these 1s2, 2s2, 2p6, plus what's written here to get the full electron configuration. So as you can see, just like in that chart above, it just increases by 1 electron each time. 2p3, 2p4, 2p5, 2p6. Okay, the other thing to notice is that in a column, they have basically the same electron configuration, just one level higher for their valence shell. So like in the noble gases, those are all going to be whatever row it's in, 2 or 3 or 6, S2, P6. In the oxygen column, those are all going to be S2, P4. This is why they have the same chemical properties, because they have electrons in the same valence shells and even really the same orbitals, just one shell higher. So oxygen looks like this. Sulfur looks really similar. It's just that that valence shell is one higher, okay? So in this one, you've got 2 in the S, 2 in that first P, 1 in the second P, 1 in the next P. Same thing here, okay? All right, let's go back to this abbreviation thing and kind of how that ties in with core electrons. So Kr has 36 electrons, and this would be really cumbersome to try to do without using the periodic table, but this one time we're going to do it. So I'm just going to start by writing. Now, I would definitely use, this chart to remind you of the order. So let's just do that actually. 1s, 2s, 2p, 3s, 3p. Okay, that's the highest we should need. So let's just copy that order and bring it down here to write the electron configuration for, oh, I don't know if that worked. Guess we'll see. No, it did. Okay. And then we're going to fill them in. So 36 electrons. Remember, the S can have 2. The P can have 6 because it has 3 orbitals. So 2, 2, 6, 2. Let's see how many we have total so far. Oh, did I not give us enough orbitals? I may not have. Yeah, I didn't. We have to go up one more. All right, let's go back to this, because that's not going to give us 30. You know what? Let's actually just fill in the electrons here and write the electron configuration from here. Okay, 36 electrons. So just start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Okay, so that is the 36 electrons of krypton. And now we're going to summarize it in the electron configuration by going in order: 1s, 2s, 2p, 3s, 3p, 4s, 3D, 4p, and indicating how many electrons are in each of those. So 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 3 electrons in the 2s, sorry, the 3s, 6 electrons in the 3p, 2 electrons in the 4s. Remember, 4s comes before 3D because its shape allows additional access to the nucleus. And so it is typically slightly lower in energy than the 3D. Okay, 3D 10, 4p 6. So this is the full unabbreviated electron configuration for Kr. So let's just go ahead and copy that and move it down. Down here. Okay. All right, so let's look at where rubidium is on the periodic table. Okay, here's Kr, here's Rb, so it's one more electron. And if we wanted to write the electron configuration of Rb, we would start just like we did for Kr, and we would literally write everything the exact same, and all that would be different. So I'm going to copy that again over because we would do everything the exact same. Let me show that to you in the diagram here. So if we wanted to, oh, this is lame because this diagram doesn't include the 5s. The 5s is right there. Well, actually, this is hard because it's slightly lower in energy between the 4p and the 4d. So like right here maybe? That's probably good. Okay, so this would be Rb. So if we went to write the electron configuration, we would write everything the same, and then we would add 5s1. Okay, so back down to here, all we do is add 5s1. So because we're just repeating everything from the previous noble gas, now we use the noble gases because those are the ones that were most sure of their electron configurations being perfectly correct because they're completely filling that valence shell. So instead of writing all of this over again, we are going to write Kr in brackets as like a substitute for this entire thing. So it's like we're basically saying rubidium is the same as the electron configuration for Kr plus 5s1. So this is the shorthand or abbreviated way to write the electron configuration. And it's much easier once you are going past, you know, the first couple rows because it just gets really tedious to write all of them. Okay, so we'll do that a lot. Also, it's really easy to identify the valence electrons then. So we can really quickly look at the symbol for that noble gas that's up to that point and say those are all the core electrons. These are the only valence electrons. Sorry, I guess I should lock that screen so it doesn't turn. Okay, so we've talked about this already. We don't need to go through that again. What we're going to do as the last thing is use a full periodic table to tell us in an easy way how to identify the electron configurations. Because like we said, in a column, they're very similar. And in a row, they all have the same n value. And every time we move a block, we're moving one additional electron. So if you remember, I talked about this like a long time ago, at least a week ago, maybe more, about how we can identify different blocks on the periodic table that correspond to where the highest energy electrons in that element are. So any element on the periodic table, we can identify it physically where it is on the periodic table. So let's say like sulfur. And now, without even looking or thinking too hard, just by seeing where it's at, that it's in that P block, we know that's where its highest valence electrons, or where its highest electrons are. Its highest electrons are in a P block. If we go back to the row that it's in, we can see that they're in the 3P. And then if we want even further information, we can count the columns into the P block. So how many columns into the P block is it? 1, 2, 3, 4. And now we have basically the entire thing. We know that the outermost electrons, like the highest energy, this isn't the complete valence shell, but the highest energy electrons are 3P4. The row it's in, the block it's in, and how many spaces into that block it's in. So again, aren't you guys like so amazed at how beautiful the periodic table is? This is why we're like obsessed with it as chemists, is because it just contains so much information. All right. Now these electron configurations that are listed here are just the valence electrons. We're going to figure out how to do the complete electron configuration knowing where these blocks are. Obviously, these won't be labeled for you on your periodic table, so you're going to have to know how to determine them. Now, there is one little oddity that we have to talk about. You can come back to these like steps as needed. Obviously, I'm going to go through them as we do it. Okay, so here's the oddity, and it actually should make sense because we said that the d orbitals are slightly higher in energy than the s orbitals, right? So when we go along the periodic table, so like if we're trying to identify, let's do an easier one and then we'll do a more complicated one. So like, let's do chlorine first. If we wanted to identify the electron configuration for chlorine, we would start at the beginning of the periodic table and say 1s. Now, in this case, helium really should be over here, okay? So we should say 1s2 by starting at row 1, the S block, and we're going to fill in those 2 blocks. So that's why it's 1s2. Also, because those first 2 electrons will fill the 1s orbital, and you can only have 2 electrons per orbital, so 1s2. Now we go to the next row, because that's all there is in the first row. 2s, 1, 2, 2 blocks, so 2s2. So we're going like this across the periodic table until we hit our element of choice. So now we go all the way across to the 2, but now we're in the P block, and we fill in 1, 2, 3, 4, 5, 6. So this is no different than what we've done before. We're just using the periodic table to kind of guide us. Now we go to the next row. 3s2. Continuing on, 1, 2, 3, 4, 5, 3p5. Okay, so this is how we're going to use the periodic table to kind of guide our understanding. Now, if you wanted an easier version, and this is completely fine, you're just going to go, unless I tell you to write the full electron configuration. But for an abbreviated version, you go up one row to the previous noble gas. In this case, it's neon. And instead of writing all of that, we just write neon in brackets to abbreviate 1s2, 2s2, 2p6. Then we write the rest. So 3s2, 3p5. So this one's the full electron configuration. This one's the abbreviated electron configuration for chlorine. Okay, what about the Ds? I think we did titanium in class on Wednesday. So if we want to continue past chlorine, we would fill in. So let's use the not abbreviated one. So I'm going to keep going here. So let's just continue on. So instead of 3p5, we're going to fill that in and go to 3p6. Go to the next row, 4s2. Now we're in the D block. It's really tempting for people to think that that's 4D. It's not, okay? We have not done the 3Ds yet. You can tell because we did 3s and 3p, and then the 3Ds haven't come. So this is true of the Ds and the Fs. They will always be one principal energy level less than the row that they're in. So this is 3D, this is 4D, this is 5D, and this is 6D. The Fs are actually 2 below their row. So the Fs fit right here. And so this is technically row 6 and row 7. But this will be 4F and 5F. Okay? This is how it should look. It would not make any sense if that was 4D because there are 3D orbitals and they haven't filled yet. So when we do titanium, we say 4s2, 3d2. And that's the electron configuration for titanium. Now, if we wanted to do the abbreviated one, let me get rid of some of these scratchies. If we wanted to do the abbreviated one, we would go to the noble gas, that's the row above. So this one, which should be argon, right? My head's so mushy today. I need to like verify that. Yes. Okay. I thought I was just tired on Wednesday. I came up with all these excuses. Apparently I was just getting sick. It hit me Wednesday night, Thursday morning. I was like, oh crap. And I always think I'm going to be better. Like, oh, it's just going to be a day. And then today was a little bit worse, which is why we're not having class. I'm sure by Monday I'll be fine. I'll stick it out if not, because I think I need to be there to do my hand gestures to talk about size of atoms. All right. So this whole thing is how you would say argon, right? If you were to do the electron configuration of argon, that's what it would look like. So I'm going to abbreviate that by saying argon in brackets. And then for titanium, I'm going to tack on 4s2, 3d2. Okay? All right. Pause, do these two, and then come back and check your answers. So the first one is a full electron configuration. The second one is abbreviated. You'll want to look at a periodic table so you know where these guys are too. Okay, hopefully if you paused, now here's your answers. I think I showed you that one already when I was talking about how it's very similar to oxygen. Yeah. Okay, and then for bromine, abbreviated, so we're going to use the noble gas above, in the row above. So bromine is right here. So it's really similar to chlorine, but one row down. So argon, sorry, so it's 4s2, completely fills in the Ds, 3d10, 4p5. Let's just look at that one really quick. Bromine, circled on there. So starting with argon, next row, 4s2, we have to completely fill in those 3Ds. That's where all those extra electrons come from. Like if you look at the number of electrons in chlorine versus bromine, like look at fluorine, chlorine, and bromine, right? Fluorine to chlorine goes up by 8 electrons, but then chlorine to bromine goes up by 17. Those additional 10, that doesn't sound right. It goes up by 18. Those additional 10 electrons come from those d orbitals. That's why you have such a jump in both protons and electrons once you hit that passing through those d orbitals. Okay. We've already talked about the S and the D. So I told you this, and you guys just need to know that there are irregularities when you get to the transition metals. You do not need to know what the specific irregularities are. But I do expect you to know that, like, they aren't always what we would predict. So, for example, like if you look at 4s2, 3d1, 4s2, 3d2, 4s2, 3d3, those are what we would predict, right? It's just tacking an electron into the d orbitals. Chromium is weird, okay? And this, again, is because the 4s and the 3d, we say that the 4s is lower in energy, and it usually is. But the real thing is that they are just so close in energy that sometimes they do funky stuff. So like with chromium, okay, I'm just drawing 4s and 3d. So we've talked before about how there's a stabilizing effect to having a completely filled subshell. There's also a stabilizing effect to having a half-filled subshell. So we would expect chromium to look like this. 4s2, 3d, 1, 2, 3, 4. But instead of doing that, this electron moves over here. And what that means is that we now have a half-filled subshell for both the 4s and the 3d. Really, it's trying to minimize electron repulsion. This doesn't usually happen between subshells because they're far enough separated in energy. But the 4s and the 3d are just so close in energy that this occurs. You also see something similar with copper. So one of those s electrons jumps up to the 3d. So knowing that this happens is important. Knowing the specific ones. I'm not going to say which transition metals have an unexpected electron configuration. But if I gave you these electron configurations, you should know that it's okay that they don't match exactly because they're in the transition metals. And maybe even that you might know that the reason why that is because that the 4s and the 3d are really close in energy. And so there's this kind of variation between where the electrons end up going in order to be lowest in energy. So due to the fact that they're just very, very close in energy. So if I was to draw this energy diagram accurately, I should actually probably put this 4s line. Sometimes it's here. Sometimes it's right there, barely below it. Okay, so there's some examples. We've talked about this extensively, the fact that things in the same column have the same properties because their valence electrons have such similar electron configurations. And then the last thing we need to talk about is ions. Oh, we did kind of talk about this already. This is related. This isn't what I was... Yeah, that's the next one. This is why they form the ions they do. So if we look at the group 1, they all lose 1 electron because their outermost shell is an S1. So it loses that 1 electron. The second one, the outermost shell is S2, so it loses those 2 electrons. S2P for the third one. And then when we get to S2P3, that's when they start to gain them. So this one gains 3 electrons in order to match the noble gas. So it would be S2P6 once it gains the electrons. In fact, the ions that are shown here, once they have gained those electrons, they all have a configuration of S2P6. So let me show you what I mean by that, by this example here. So if we want to write the electron configuration for something that has gained electrons or lost electrons, we just need to gain or lose that number of electrons and do it just like we would do any other electron configuration. So aluminum normally has 13 electrons and sulfur normally has 16. So 13 electrons, 16 electrons. That's what their neutral atom is. If it loses 3 electrons, the aluminum, it becomes 10 electrons. If sulfur gains 2 electrons, it becomes 18. Okay? So aluminum loses these ones, and sulfur gains 2 here to become 3p6. So what's really happening is all of the ions are ending up with S2p6. It's just whether they're going down to the next subshell down or whether they're increasing to go complete that subshell. Okay, so do the homework that you can with electron configurations over the weekend. Some of the stuff we did on Wednesday, I really just don't like that they present that so early. So we'll definitely go over this stuff again. The whole notion of how how the shielding affects the ability for the outer electrons to feel that nuclear charge, how that affects how close they can get. We'll all go through that again when we talk about the size of atoms, which we're going to do on Monday. So like I said, just try to do as much of the Chapter 9 homework as possible so that you're up to date. Okay? Have a good weekend.